lab, and you'll be seeing a lot more of her. I also wanted to thank Idaho Power. They're our sponsor for BSUG, and they provide the lunch, so enjoy that as well.
Thanks, Katie, and thanks all of you for coming down. There's three more BSUGs coming up through the summer and fall. Just give a plug for those real quick. Jake Dunn is returning to give us a presentation on October 7th. And then at the end of October, I think it's the 28th, Roderick Bates from Karen Timberlake will be here. And then it'll be, it's sort of a to be determined on that final BSUG. Katie, and again, thanks to Idaho Power for providing the funds for this program, among others. I think that it's a great contribution to the A&E community, and we appreciate that. And thanks to Katie for introducing and passing off the baton she just left. But and then I'd like to take just a couple of quick minutes because we want to get going with real content to talk about Corey Squire, our guest today. He is currently with Lake Flato in San Antonio, Texas, a firm with which I'm sure many of you are familiar. They do a lot of prominent work. You see them published quite a bit, really terrific stuff. He joined them 3 years ago. He came from SQ Dumas Ripple EDR in New Orleans. He ended up in New Orleans by accident, on purpose, and stayed by accident. I guess he is a graduate with a degree in environmental science from Oberlin College in Ohio, and he finished that just about the time that Hurricane Katrina hit and devastated New Orleans. So he went down to provide some assistance in the reconstruction and disaster relief, and ended up staying and going to Tulane to get his MArch, and then staying along for work with EDR. So we're pleased to have him here. He does, what's your official job title? Sustainability? Yep. So he's the guy that was at EDR doing it, and now he gets to do it for Lake Flato. So thanks, Corey, and take it away.
All right. Is that good? Yeah. Can you all hear me? Because this mic doesn't work in this room. Let me know if I'm not speaking loud enough. But quickly, I want to start off by giving an overview of Lake Flato, who we are. We are a firm out of San Antonio, Texas. We were founded 30 years ago. This is our current firm profile that the marketing department gave me. We have 94 employees, which is the most we've ever had. We're hiring pretty frequently. Apparently 7 couple. Everybody in the office is dating each other. Really important to who we are. We have a huge, for San Antonio, I don't know if anyone's ever been to San Antonio. It's not a very cycling-friendly city, but almost half the office bikes to work every day, which is pretty exciting. When not riding, we have plenty of efficient vehicles. And we do this big retreat every year, which I think I have a picture of. Oh, no, sorry. We've also won 8 National Committee on the Environment awards, the COAT awards, and we're very proud of the high performance nature of our projects, and really kind of place-based design, whether they're in Texas or whether they're in other regions of the country as well. This is where we work. The majority of our work is in Texas. Well, maybe about 50% of our work is in Texas, and the rest of our work is scattered all over the country. We have a few projects in your region, which I'll touch on. We also have a few projects in Mexico, and recently we have some international work in the Cayman Islands and the British Virgin Islands, some other Caribbean things. This is a project. It's called the Hill Country Hakal. It's one of the very, very early projects. This was built probably 25 years ago, and it kind of set Lake Flato on the path of climate responsive and site responsive design. This is an unconditioned kind of vacation home in the Texas Hill Country. The materials are all basically local. The wood was harvested near the site, and kind of all, and it's unconditioned, so there's a large comfort range in this project. There's a wood stove and a fireplace for heat, but no conditioning at all. And this is kind of where we get these ideas of, or kind of the basis of the firm is kind of looking at what's available and building just really simple, looking at vernacular styles from different areas. Today we do a little bit more of a thorough analysis. This is kind of a typical climate analysis that we'll do early on in a project. We're looking at views, sun angles, wind angles. This is actually a page from our toolkit which explains how to do this to designers in the office. But then my role in the office as sustainability coordinator, what I like to really focus on is actual performance. It's the kind of the most important thing to me is after we complete a project, how's it actually performing in the real world? What do the energy bills look like? How happy are the people? So we work a lot on simulations to get up to this point, but I spend a good amount of my time reading meters, and I think this is incredibly important for all architects to do is kind of get in the field and read some electrical meters. You learn a huge amount that you'll never get from kind of the design side of the project. So here's a quick profile of our Mountain West project. Just a few to run through. This is the Prim Library in Nevada. The first 15 years or so of the firm, a lot of the projects were focused in the Texas Hill Country because that's where we were from, that's where our inspiration's from. And then when we started to move to other regions and other climates, we took a little bit of kind of our knowledge of the Texas Hill Country with us, but also looked at the local environment as well. The idea behind this project was really, this is in a heavily wooded area. We don't have trees like this in Texas. So really focusing on timbers, kind of thicker members, and then columns that almost make you feel like you're in a forest, similar to the pine trees outside. Another project that we've done, this is LC Ranch in Montana. This is a more recent project, and we have two components of this. We have over on the left, we have the pavilion, which is the living space, and we have these bedrooms, which are tucked into the mountainside or the hillside, and they have sod roofs for insulation. A little bit of an aerial of what this place looks like, kind of in the middle of nowhere. This is the living pavilion. This is where the kitchen, the living room, the dining room is. And the idea is, again, taken from kind of our Texas idea, that everything is basically a pavilion. The pavilion idea is something that when it's nice outside, you can kind of completely open the space. But because this is a cold climate, we also have these sliding panels. So during the winter, you can close the glass sliding doors and then close these insulated panels over them to kind of shut down the building and make it a little bit more thermally conductive to the climate. And then the bedroom wing, a lot less glass, fireplaces as a heat source. But I guess back to the pavilion right now, just a completely open environment. You can really enjoy the summer when it's nice outside, open everything up, and again, it transforms in the winter to kind of account for the really harsh climate here. Even though I shouldn't point this out, we have a lot of metal going through our facades. So it's something that we're working on, and we don't do this anymore. So I just wanted to make a point of saying that. Another project is in Sun Valley, Idaho. This is a pool pavilion, which is off of a swimming pool at a ranch. And similar, the idea is kind of this can be completely open so that when it's nice outside, we provide comfort with air movement through fans, through ventilation, and then in the winter, the building can transform a little bit, become a little bit more insulated and keep people warm in the winter. So houses are something that the firm does a lot of. Right now, our projects are about 50% residential, 50% commercial. We do a lot of different building types. Higher education and urban development are things we've been focusing on a lot recently. But we also do boutique hotels, schools, mostly private schools, a lot of visitor centers. But the houses are kind of really interesting to me because the project life cycle is so short that you can test new ideas. It's also a lot easier to sell concepts to residential clients when you don't have a board of directors focusing on these things. So a lot of the kind of things that I'm going to go over, we've been experimenting with on residential projects, but they're all applicable to commercial projects as well. And And when we kind of have the data that systems work for residential projects, we can move into commercial projects with similar ideas a lot more easily. So why houses? From a sustainability or energy standpoint, why houses? This is kind of a graph. I'm sure everyone's seen this from the 2030 challenge. Buildings use almost 50% of the energy in the entire country, so focusing on reducing energy in buildings is incredibly important for battling global warming, greenhouse emissions, all those things. But if you divide out the building sector, about 50% of the projects, 50% of the energy use in the, 50% of the building energy use comes from residential, so about 25% of all the energy use. So it's a significant energy kind of source. The spacing got messed up a little bit. But at Lake Flato, we signed on to the 2030 challenge. A lot of other firms in the country have as well. Are people familiar with the 2030 challenge? Commitment that by 2030, our portfolio will be net zero, and we're stepping down a little bit every year. We're right now in the 70% reduction, so we have pretty high kind of goals for our projects. We want to get 70% reduction on all of our projects on our way towards 2030. So typically, this is how we start a project. We look at massing studies, maybe come up with a few different schemes, analyze them under a few different metrics, maybe energy use. We're looking at total annual energy in kBTUs on this one. And then we'll run some really, really simple conceptual energy models at the beginning. This is Sapphira. I don't know if people have used this software before. It's not a very good software, but it's great for people without energy modeling experience to kind of get their hands on some of these concepts for the first time. We use a lot of different software in the office. RemRate, specifically for residential projects, is what we're doing. But what I came to realize about a lot of the simulations we're doing is that the building simulation software, at least the energy models that we've been using, these kind of packaged pieces of software, they all ask basically the same questions. They focus on things like insulation value, ventilation rates, glazing performance, window wall ratio, all these kind of things. And we've actually gotten very good at kind of dealing with these inputs. But there's some other things that have been surprising us. So we'll jump into a case study. This is a project called Hogpen Creek. This project is in Austin, Texas. It's a single-family residence. It's a part-time residence. The family has a house in San Francisco and this house in Austin, and they spend about 50% of the time in each. They travel back and forth almost every week, so it's not really a seasonal variation. Sorry? That's nice, yeah, I know, right? They're not architects. But yeah, this project is about 2,300 square feet. It's divided, it's arranged where we have this large living space over here. I know the axis is wrong. It's north-south facing, but there are a few ways of covering that. We have some trees and some shading strategies. And then we have this wing over here, which is our guest houses. 2 guest bedrooms. There's an exercise room, which can double as a 3rd guest room. And there's this outdoor porch over here. And the project is right on Lake Austin. So kind of if you drive in here, walk down that path, you're already at the lake. And they have this little boathouse that kind of sits on the side over here. The entryway to this project, where you're walking right through, to your right, when you're walking down this pathway, is the guest wing, kind of occasional used spaces. And then that large house over here is the main house with a swimming pool that's almost kind of a moat. There's a little step where you walk over the swimming pool as you're going towards the house. This is the screen porch on the north facade. There's a whole bunch of different options for outdoor spaces in this project, which is nice. The occupants enjoy that one. An interior view, again, you can see the swimming pool off the side. And here's our major sustainability strategy for this project. These 2 bars I'm talking about, we have our main living bar. That's going to be occupied about 50% of the time when the occupants are there. And that has an open loop geothermal system that comes directly from Lake Austin. A lot of the houses along Lake Austin can use the lake for either geothermal heating and cooling or for irrigation. And then this system heats and cools the house, also heats the hot water, and heats the pool as well, which is right over there. We have a completely different system for all of the partially utilized spaces. For the guest houses, which may only be occupied I don't know, 2 or 3 times a month, if even that much, maybe even less. There's mini splits where the system can be turned on if you're there, turned off if you're not there. All the water is instant hot water, so there's no tank in those spaces. It's going to just kind of constantly heating water. So we thought that we had this kind of down pat. We had all these great strategies. It was supposed to be this great performer. It was a small house, 2,300 square feet is pretty small for custom kind of luxury projects, and we had a budget of almost $1,000 a square foot, which is why we were allowed to use some of these systems. So we were pretty excited about this. And then a year rolled around, and we got our energy bills, and we started looking at them. So here's our monthly energy bills. This is kind of where we expected to be, where the energy model showed us we should be. But we were nowhere close. It was kind of, the energy budget was kind of exploded upwards. We didn't even really understand why, because if you look at the highest month, it's January, which is not what you'd expect in Texas. You'd expect July or August to be the highest month. I mean, the swing seasons made sense, but it was kind of weird. We didn't really know what was going on. My first thought was the mechanical system must be working terribly. Maybe it's this thermal bridging. Who knows? We started, but we were going to kind of go in and find out was the plan. We started looking at our other projects as well, and we started comparing our predicted energy use against our actual performance, and we found this huge variation. So this is Hogpen, the one that I was just showing you, where the energy use is probably 4 times higher than we were thinking. This project, which we'll also talk about, Uvalde, about 50% more. And then we have one on Long Island in New York, again, probably 4 or 5 times the difference. So we purchased these e-monitor systems. It's an energy monitoring system. It has a CT that clips onto every circuit. I don't know if you, I mean, I'm sure you've used or are familiar with CTs, but this particular system is nice because there's a user interface that the clients can interact with. And you can monitor up to, I think it's like 48 circuits per panel, which is pretty useful because we have some big panels. So I went to these projects. We installed all these monitoring systems. And this way we can find out kind of not just when the AC is on, but also when they're using their toaster, like when the closet light goes on. Like every single watt in these projects, we were going to know where it came from, which is really, really exciting. This is kind of what the setup looks like from the exterior. All the CTs are tucked away inside of the panel boxes. That speaks remotely to this gateway, which connects to the wireless internet and then broadcasts the data in real time. I think it updates every second, so that you can access this data anywhere in the world. I can be at my desk at my office and watch the hot water spike and know that the client just took a shower. It's kind of weird, but you can call them if they shower for too long. And then we're also monitoring the temperature, humidity, and CO2 in all these projects as well. CO2 is a great proxy for occupancy, so we can tell if they're using energy when they're there or when they're not there, or if there's any difference between when they're there and not there. So depends on the project. This project we only have one, and it's in the main space right outside the. This is actually a closet right next to the pantry, right outside the kitchen and living. Some of our projects, which are multiple buildings, will have multiple sensors. We're not doing kind of a really granular interior environmental study where we're looking kind of space by space in the same broader thing, but it's something that hopefully we can work on in the future. And this is what we found. This is how the energy use breaks down for that project. The HVAC all the way down here. From an HVAC perspective, the house is incredibly efficient. And it makes sense because the envelope was, we have a few instances of thermal bridging, but the envelope is relatively good. We have rigid insulation on the exterior. It's a pretty compact footprint of the main house. And the geothermal system was pretty efficient. Lighting, kind of weird for lighting to be higher than the HVAC, but we'll look at that in a minute. And then appliances and domestic hot water were kind of on par. Now, what kind of blew up the energy budget was the fact that we had this pool that was using, it was about 40% of the total energy of the project was this pool, maybe even more at this point. And then we had a few other things that we never accounted for. There's a security system at this house, which has cameras, and the cameras are burning 120 watts constantly, kind of all through the year. The irrigation system, we had water being pumped out of the lake to irrigate the front lawn. Most houses have pressurized water delivered to their house, so there's no energy use for irrigation. And there's the boat lift, and I had no idea how to model a boat lift, so I didn't. But if we compare the kind of the energy end uses in yellow on the left side, that are, or I guess the blue on the left side is kind of these typical inputs that you put into an energy model compared to these other uses, the pool and these other systems. The pool and the other systems are more than the rest of the house. So it caused us to kind of rethink how we're thinking about energy models, and what we're including and what we're not including and what we should be focusing on, kind of where we're focusing our efforts. So looking at the REC, the Residential Energy Consumption Survey data for the past 30 years or so, over time, the percentage of a residential project's energy that goes towards the HVAC system has been decreasing at a pretty consistent rate. These are kind of the 4 points, but they line up very well on the trend line. The lights and plugs percentage of the energy has been increasing. Now, the total energy of the projects have been decreasing. But this is kind of really significant because 30 years ago, when the firm was founded over here, HVAC was incredibly significant in terms of the overall energy of a project. And now it's kind of on par with some of these other things. If you extend these trend lines forward, somewhere in the vicinity of 2019 is when we'd expect the typical house to have plug loads and lighting loads that are higher than HVAC loads. And that kind of makes us rethink about where we're focusing our efforts. Of course, the reason for this is that systems have gotten more efficient, the codes have gotten more stringent for the envelopes, and we also have more things to plug in. The things that we're plugging in are more efficient as well, but we have more of them. So we have the typical Lake Flato house. This is 6 or 7 projects that I was able to get data on. We're already in this realm where the lights and plugs are going to be significantly higher than the HVAC system. So it might happen in the future for kind of typical houses, but custom projects are probably already there. So going back to this one, we got this beautiful pool, but then we look at how it's performing. And you see this is the pool pump, this blue color over here, and it's running at a constant 3,000 watts, which is crazy. And then another 4,000 watts on top of that for the pool heating. This is the system that, because it was geothermal and it was efficient for the house, we imagined it would be efficient for the pool. See these little kind of teeth that are taken out of the pool heating? There's only one system. There's one geothermal system, and it heats both the pool and the house. So these, when it's not heating the pool, this is when kind of it switched over to the house mode. So that 90% of the time the system is running, heating the pool in the winter. And then about 10% of the time it's working for the house. So this is why when we were looking at the total energy use before, the highest month of energy use was January, not July or August. The lighting was another kind of abnormally high energy use for this project. And we were able to look at that on kind of a minute-by-minute basis as well. And they have a Lutron control system for this project. So all the lights in the house were designed by a lighting designer in collaboration with the control system. And the lighting designer set moods. And the mood is like, at this time of day, these lights will go on every day, regardless of whether you're in the room or not, regardless of whether you're in the state or not. So, so this is what, every single day, this is what the lighting load profile is. You can see this is actually cut off, but it actually goes up. This is 4,000 watts up here. Yeah, 4,000 watts of kind of connected lighting load goes on every day for 6 hours between the 6 hours, the 8 hours, 6 o'clock at night to 2 o'clock in the morning. So studying this project, I had no idea when the occupants were even home or not. The only way that I can tell is if the stove turns on. Everything else in the project is automated, so things go on and off predictably the exact same at the same time every day, regardless of occupancy. And then the last thing is you can't really see it, except right there is the video camera. And this is kind of the load on the video camera. Less so than the lights, less so than the pool, but still significant. 8% of the total energy of this project goes towards the security system, which is crazy when you think about it, because we spent all this time looking at insulation values and say we can add another ½ inch of rigid and we can decrease the project's energy use by 2%. And then the AV contractor sells the security system to the clients and they're like, fine. And we never even think about it because I don't have a security system in my house. I don't know how much energy they use. But now it's something that we're learning, and now we know which questions to ask for our new projects. When the AV consultant is selling kind of high-tech security systems or other control systems, we now know to think about their energy use. We modeled the pool in terms of energy for the pump, but not in terms of energy for heat. And the reason why is because, I mean, it was just a complete mistake on our part. We didn't even think about it. The pool heating showed up a little bit later in the project. They didn't initially ask for it. And then we didn't add any additional equipment for the pool because it was basically the same heat pump that was controlling the house could just switch to the pool. It's now something that we know that we need to model and be more serious about. And also the way we modeled the pool, this is way, way more energy than we expected for the pool. So, and I'll get to that in a second as well. So we looked at all these different uses, what's being used right now, and what we imagine based on operational changes alone, how we can decrease the energy use of this project. And we prepared kind of a report for the client with a series of recommendations. And we think that we can get the total energy use down with no design changes, just operational changes, by about 54%. And that puts us pretty much in the same range as a typical Texas house, which is pretty exciting because right now we're about 3 times as much. And if the pool wasn't even included, we would even be running more efficiently than a typical house, which is exciting. To go back to your question, modeling the pool, this is after we were able to readjust the pool pump and kind of get some things straightened out. This is how the pool is running now. Instead of 3,000, 2,000 watts for 4 to 6 hours a day. It's a energy savings of about 80%, a little bit more than 80%. And this is pretty close to what we expected the pool energy to be. But before we sub-metered the project, we had no idea that the huge energy bills were the pool, right? Because the pool was a very simple thing in our mind. You just got to turn it on, right? It's supposed to follow a schedule. It just wasn't following a schedule. It was constantly running. The clients didn't know what their energy bills should be. The clients didn't know how often a pool pump should run because it was really our responsibility. So this is kind of a pretty cool victory for us. So of that 54% reduction in energy, we're already about 30 to 40% of the way there, and we're still working with the client to kind of get the energy uses down. Lighting is going to be the next big thing to tackle. Another case study, this is a house in West Texas in a city called Uvalde. We call this the Uvalde Ranch. It's a little bit more rustic. The previous project was more of a modern feel, but very, very similar with exposed structure, with some materials that are local to the area, a rain chain feeding into a reclaimed metal, an old sugar boiling pot. Has a water feature. This is the interior. It's a very small space. It's similar size, actually. It's about 2,200 square feet, though a much, much, much lower budget. They didn't have all the fancy control systems that the previous project had. There's some reclaimed rafters in the ceiling. But they did have a pool. So again, this was kind of at this point we knew that it was subject to some problems. So we hooked up the same system over here, and we found the same problem. We found that the pool is running at a constant 2,100 kind of watt average, 12 months out of the year, 24 hours a day. And the pool was beautiful. There was never any moss buildup on the pool, right? There was never any problem with the pool except the energy use was a little bit high. When I first contacted the client, before we knew that the pool was the problem on this project, the client told me that the energy use was higher than she expected. And she explained to me that she's very energy conscious. When she's not using her toaster, she unplugs it because she's heard of phantom loads and she doesn't want to use energy on the toaster. But in reality, it was her pool pump, which was running at 2,000 watts a day, and it wasn't the toaster, which doesn't even have a phantom load. So that goes back to just client education, right? The clients want to kind of, I mean, they want to save money, but they also want to do the right thing energy-wise. But if we don't give them the tools to do that, if we don't give them the knowledge to be able to do that, it's not going to happen. Lighting was a similar problem in this project. Much, much less significant than Hogpen. Hogpen, we were burning 4,000 watts a day. This project, pretty typical lighting. Except this one room called the library in this room had much, much higher lighting than every other project. And we went back and checked the lighting power density on this, and we had an LPD of 2.31 for just basically a living room, which for a reference I put there that it's higher than what's recommended for an operating room in a hospital. And this is actually just because the lighting installer told us they were installing one thing and installed another thing. And we never went out to verify, which we should have done because that's using whatever amount of energy more than it should be. So we did the same thing on this project. We looked at all their uses. We figured out what they could decrease their energy use by. And we showed them that they have the potential to save about $3,000 a year by making a few changes. And they were all excited about it. And we told them they can keep leave their toaster plugged in. But maybe we would look at the points. So we were able to model the project based on both the inputs that we already knew and based on the data we've collected. We were able to model the project to make an estimate of how the set point would affect overall energy use. So they set their house to 70 degrees. So they said maybe in the summer set your house to 71 degrees. You could save 4% on your total energy use. And if you're uncomfortable, just switch it back. But if you're comfortable, maybe you try 72 degrees. And we worked through this process with them for the month of August. And they ended up liking 73 degrees. They tried 74 and it was a little too hot, but they were perfectly happy at 73, which gave them something like a 10% energy reduction for their HVAC, which was kind of exciting. But it did take kind of this constant working with the client, kind of explaining the systems that they had, explaining their options, giving them kind of the power to make these decisions and understand the implications of the decisions that they're making. We also talked about the difference between setting back the thermostat as opposed to just turning it off, and depending on how long they're going to be gone or their expectations when they return, is it better to turn off the thermostat entirely, or is it better to turn it down to a lower set point? This is actually an experiment that I did at my house, where for 1 week, it was July 2012 maybe, for 1 week, every time I left the house, I turned the system off, and every time I came home, I turned it back on. So this is kind of like the spikes that happen when I turned it back on. And this next week, which had very, very similar temperature, I set back the thermostat to, I think I set it to 80 degrees for that week. And you can see that the spikes are much higher when it goes from when I come home and it's 86 degrees and I have to bring it back down to 78. The spikes are higher, but overall, this week I used 50% more energy. So again, we can kind of push the boundaries of what people think they should be doing and experiment on each project as a case-by-case basis to find kind of these optimal kind of operation criteria. This is also something that's applicable for commercial projects as well. Instead of having a homeowner you're working with, there's a building operator, and they can do the same thing. We can see how many kind of temperature complaint calls we get at this temperature, and then we can experiment with another temperature and see where we end up. So same thing here. We were able to reprogram the pool. We were able to save, I think it was 70% of the overall energy or 70% of the pool, but 40% of the overall energy for this project by just reprogramming the pool. This is the day that we first plugged in the e-monitor, and you can see the day that we had the pool reprogrammed. So it was a pretty big victory for us. What was exciting, again, was this was not an input that we typically think about, but it was something that is incredibly effective in getting energy use down. And had we not come in and do this, the pool would still be running at 2,000 watts a day because they didn't know there was a problem a little bit higher than they expected. And by a little bit, they were comparing it to their previous house, which didn't have the nice systems that we had. It's actually a lot higher than what they're having now. So energy signatures are a tool that we use to compare projects across sizes, across kind of geographic regions. Houses are such kind of a one-off thing where it's very difficult to, across a portfolio, compare the performance of projects. There's just so many variables. Years are different in different climates. So are people here familiar with an energy signature? Has anyone used these tools before? Okay, so I'll go over how we're using them. This is Uvalde Ranch, and what we did is we plotted the total energy used every day against the average temperature for that day over the course of a year. So the first thing that we did is we saw we had a few outliers. Christmas Day, there was much higher energy use. On this one day, whenever that was, the low energy use, the pool stopped working, and they called the pool people, and they came out and fixed it. But it's kind of interesting just to see that everything else falls in a very, very predictable pattern. By just throwing in a simple polynomial, we get a curve showing kind of a steepness or an incline in the summer, another incline in the winter, and then we have this kind of plateau over here in the winter. Sorry, in the swing season. By plotting to both axes, we can see that the base load, basically how much energy is used on a typical day, not counting whatever is temperature dependent, so not counting the HVAC system, about 64 kilowatt hours a day. We can also plot downwards from the lowest point in that curve and see what the typical, which is about what the balance point of the project is. So the balance point is about 50 degrees, which to me says is a fairly good envelope, actually a pretty good envelope. So just kind of to go over those for people who are less familiar with this process. A typical energy signature, you imagine that everything from above the lowest point of the curve is temperature independent loads. These are the lights, these are the pools, these are the computers, everything else. And then heating and cooling are the kind of the area underneath the curve that slopes up in the warmer temperatures and lower temperatures. So what's cool about this is even if you're not sub-metering and you have even monthly data, you can start to draw these curves and you can get an idea of where the energy use is going. Some projects we're finding, or potentially some projects, might have a very, very low temperature independent load or a base load and very high heating and cooling loads. This would be kind of a very inefficient project with not many appliances. Or you might have a project like here, this is Hogpen basically, where we have a lot of loads, just plug loads, the pool, the security, but a very efficient HVAC system. So we have very little additional loads for heating and cooling. So this really helps us not just to diagnose buildings that exist, but also to kind of predict where we need to focus our efforts on. So this is, we have 6 projects, and we're able to plot them all together. We normalize the watts per square foot so we can compare. And what's pretty cool is you look at these 2 projects we saw before, the Uvalde Ranch and Hogpen Creek, and the curves are pretty similar. The slopes up and the slopes, or the slopes in the summer months, slopes in the winter months, are not all that different, and that tells me that we have a pretty similar envelope, a pretty similar efficiency of our HVAC system. But the Hogpen is shifted up all the way up here because this is the base load and it's huge. We have some other projects that we also included on this. I threw in my house, which is this one, and I live in a historic house in like the east side of San Antonio where I have no insulation, and so my balance point is like 68 degrees, and in the winter the slope slopes up pretty dramatically. We also have this house on Long Island, which is our colder climate. It just, I mean, you can compare houses against different climates because they should function the same at the same temperatures. For the most part, humidity is still something that needs to be taken into account. But you can see this project has a very, very steep slope over there, so it's similar. But besides those 2 projects, for the most part, our projects tend to have the same curves because we're basically using the same envelope, we're using the same details. And I've actually plotted more since then, about 3 more, and they follow the same curve, but they just shifted to different places depending on the base load. So that kind of leads to this new process that we're focusing on. This is something that we're still working on. This is kind of a project in the middle, but I've actually never spoken about these things before, and we haven't completely developed the plan of what we're doing. But the big thing that I'm trying to wrap my head around is we have this whole list of energy reduction strategies. And then we have half of the things on this list are not typically modeled, or at least they're difficult to model. And there are ways of modeling this, but we have to kind of work through what we're doing. So occupant training, we found, I mean, you can decrease the energy use 50% by occupant training, but it's not like you can slide a occupant training variable in an energy model and kind of get some result. So there are kind of new things that we're looking at. Feedback loops are another thing. If the occupant has access to the energy data in real time and they're about to get in their car and go on vacation, but they pull up this thing on their phone and they can see that the bathroom light's on and they run up and turn that off, there's a real energy savings there by having that option. But again, it's a difficult thing to model, a difficult thing to predict. So this is kind of a list of kind of guidelines we're starting to develop going forward. Identifying the pool. Every project has a pool, but it's not always a pool per se, as in every project has a large energy user that you're not immediately going to take into account. And it's something that from the beginning of the project, it's good to identify it and kind of wrap your head around how you're going to model it, how you're going to think about it. For a residential project with a pool, the pool is probably a pool. For a dining hall, which is another project that our firm is working on right now, the pool is the kitchen. It's just a very, very large energy user, mostly plug loads or gas or a ventilation load in that sense, but something that's a little bit more difficult to model than HVAC, envelope, lighting power density, those kind of things. And then base loads, all the plug loads, everything else, as I showed on the graph before, especially for residential, but commercial is also going to follow the same pattern. These loads are getting bigger and bigger kind of all the time, while the HVAC loads are getting a little bit smaller. So just earlier in the project, thinking about plug loads, thinking about all the loads that are not associated with the envelope, associated with the HVAC system. Listing those. I tend to model these guys just in Excel. Just what's the wattage, how often is it going to be used, multiply, add it up on the bottom. You can have that kind of running process all through SD before it becomes a more specific thing and a more complicated model. But right off the bat, we can see this is going to be a major issue, or maybe it's not going to be a major issue. Leveraging feedback and accountability are these other big things we're dealing with. Accountability is what we're saying now is when we first hire an HVAC contractor or a lighting designer or a pool consultant or really anybody else, or our kitchen consultant for our dining hall, we're going to tell them that we're going to track their work. They know from the beginning of the project that we're going to be monitoring everything. We're going to see where the energy use is going. If the bills are high, we're going to know if we call the lighting designer or if we call the pool contractor or the HVAC contractor. And in theory, the fact that they know this should provide us with better work and more efficient systems. Again, a very, very difficult thing to quantify, and also not something we've tested yet because we haven't started a project where we're told somebody that we're monitoring them and that project has been done yet. It'll happen soon within this year, which is exciting. But I think it's really important. Leveraging feedback is the other one, just allowing the occupant to see what they're doing, see the energy implications of their choices, and empowering them to make better choices. So the system that we use, one of the reasons we chose this particular system is because it has this great user-friendly interface. They can pull up on their phone, they can see their top 10 circuits at any given time, what are they? And the toaster has never appeared on that list. Automation and controls and time of use are two other things. This is 5 houses that we studied, a typical week where the lighting energy use is plotted on top of each other. So you can see hog pen again. Very, very, very high energies. This is a huge connected load, but it's also used all the time, where you have kind of smaller houses or smaller lighting loads over here, more typical lighting loads. So this control system may or may not have been sold to the client as an energy saving strategy. The lights will never be on during the day kind of thing. But in some other clients, it's definitely sold as an energy saving strategy. But depending on the type of automation and depending on the type of the controls, you can save energy or you can use a huge amount of energy. So the big rule that we've come up with for this is occupant engagement. Any system that increases the ability of the occupant to engage with the system is probably going to save energy. Well, any system which allows the occupant to forget about the system, like this lighting system, is going to use a lot more energy. And then time of use. This goes back to security, but also kind of lights. It's probably better to have a less efficient lighting system that's used less frequently. It's also cheaper. So if you take an LED, a 13-watt kind of retrofit LED, and you replace that with a 9-watt retrofit, a 13-watt retrofit CFL, and you replace that with a 9-watt retrofit LED, you're going to save 25% of your energy. But if you just kind of kept the lights off 50% of the time, you're going to use more energy. But the time of use thing is a difficult thing for us to think about as designers because we have control over the connected lighting load. We don't have control over how often they're used. So thinking about architectural strategies that promote less time of use. Part of that could be daylighting, daylight controls, occupant education, or other things that I haven't thought about. And that's where we are right now. So thank you. Any questions on what you've seen today? So the way we do that is, so we own the systems, the firm purchases them, and we install them, and we keep them in-house for 2 years. And the 2 years is so we can see a variation of temperature over the course of, maybe the 2 years will be the exact same, or maybe they'll be significantly different. After 2 years, we'll go back to the house, and we will offer the homeowner the opportunity to buy them from us. So if they really like the system, if they're going on vacation and checking their thing every time and they think it's really useful, they can just buy it from us. And we usually give them a discount, like 50% off, whatever, because they helped us with our research and it was exciting for everyone. Otherwise, we'll just uninstall them and take them to the next house. We currently have, I mean, the systems are all, they're all different based on how many panels the project has, how big the project has. But we have enough e-monitors to study probably 8 houses at a time, 8 typical houses, maybe 4 really big houses, or a higher number of smaller houses. But yeah, there's a rotating cycle on that. So we just started our first commercial building monitoring project with this same system. So the e-monitor system, it's actually, originally it was for small commercial, things like franchises of like, I don't know, fast food joints or something like that, where somebody might have 5 or 6 buildings and they want to be able to look from their computer how much energy each of them is using, where the energy is going, and compare across the buildings. But it's also really useful for us. So with this exact same system, we can just go set up in a commercial building. So yeah, we recently just did our first. It's a 3,000 square. Actually, we have 2 right now. We have this system set up in a 5,000 square foot open air pavilion, which is designed for a Living Building Challenge certification that we're hoping to receive next month, which will be really exciting. And then we have another one that we just put into a visitor center at a Texas State Park. And kind of the idea is, now that we have some data, we can show commercial clients the financial benefit that they'll get from letting us study all these things. For the commercial clients, we're encouraging them to buy the system because it's more complicated, it's a much bigger system, much more expensive for us, but also we think that they have kind of more opportunity down the road. If they change building operators, then this new person can come in and still use the same system. So yeah, so in the office, kind of houses are a laboratory for experimenting with new ideas. And the ideas at work, we move into the commercial projects. Well, it's really hard to go straight into commercial without some data, some assurance that the client's getting something out of it. Yes?
Do you have any specific recommendations for, or did anything come out of it that would affect how you model buildings without, if you knew you didn't have the opportunity to do some measurement verification after?
How would we model things differently?
Yeah.
The major change in modeling, just in general, regardless of what we're able to do afterwards, is really focusing on the plug loads. What we found, actually, I didn't include this slide, which I probably should have. Let me just go back a little bit. This slide. What we found on all these projects is the pool and the other loads kind of go to here. So if you don't take that into account, our modeling is actually really good, which makes sense because, I mean, there's nothing that crazy that this should be so far off. This one was the same way. We were basically right over here if you were kind of take off the pool and all the other weird loads. And this project, the Long Island one, actually was completely different. We modeled over here. The plug loads are only up here. But there was a major problem with the mechanical system on that project. So one thing that this project did allow us to do was seeing that our modeling was pretty accurate. And the ways that, and the 3 instances, were these 3 instances, 2 of them we were wrong because the plug loads we didn't account for. And 1 of them was wrong because the mechanical system was bad. And we were able to then take that data and go back and like direct where we're putting our efforts in for either future projects or to improve this one. But I would say the thing that has changed in our modeling was this plug load. basically we model plug loads now appliance by appliance, not watt per square foot across the building. And it took a lot of just kind of new information just to learn what everything uses, right? So.
And then I have one more question.
Yeah.
So do you think that, in a commercial setting, we'll do the modeling, we'll install, and then the commissioning agent will go out? Do you think that the commissioning agent should have access to the model data, or those should be more, to me it seems like that should be more intertwined because you're using your model significantly during your commissioning process
Right.
of the house. And I think right now in the commercial world that wouldn't, that doesn't happen.
It's not happening right now, it should, but I think it probably should. I think that the two things are, one thing that's exciting about this is we're also tracking interior and exterior temperatures. So like for the exterior temperatures, we can go back, during commissioning, we can go back to our original model, put in the exact exterior condition, not just kind of a PMY, and see if that changes things compared to what we expected. And also with the interior temperature, we can test assumptions on set points and on occupancy hours. But yeah, the idea for a lot of these is that we use the same model, and after we learn all these things, we update our models to get to the point where they both match, right? Like a real measurement verification. We haven't done this on a project where we had a commissioning agent yet, but the project that we just installed, the second commercial project that we just installed, will be the first one that we look at that.
So following up on that, I guess the hog pen and Uvalde, which you went into some detail about, you discovered I guess for all of them, did you discover the discrepancies between predicted and actual by examining the model? And do you think that if that's the case, do you think you would have found these problems if you had your model? So would that perhaps something like that Long Island retreat where the difference is so large,
right?
Without a model, you wouldn't have had the difference, but it would have been unusual.
Right. So yeah. So these two are kind of a different case. The model was accurate, but we just added other things on top. The Long Island retreat, which I probably should have brought more information on, because it is a separate case. The model really helped us in that more so than these two, because the problem was the HVAC system. It turns out in this project we were doing simultaneous heating and cooling, which is one of the reasons that the energy use was so high. And without the energy model, we would not have known exactly why that was happening. So yes, when the problem was specific to the HVAC system, we really got into the model to kind of retest all our assumptions, make sure that what we thought was happening was kind of what we were modeling was really what we thought was happening, and then go back to the actual and seeing why there's such a big variation. For these two, which it turned out that we were really close, it was exciting to see that we were really close, because before that we thought we were really stupid and we had no idea what we were doing because the variation is so big. But yeah, so I think that without the model for the ones with the HVAC problems, it would be very difficult to diagnose. Yeah.
So just on these projects, I guess, to start with, was there any utility involvement, any utility incentives, or did they help fund any of the cool experiments you were doing? Or
so the utilities didn't help to fund our experiments. All three of these projects have geothermal systems, and in each of these areas, the geothermal system was incentivized by the utility, which is kind of exciting to now share the data with them, which we haven't done yet. But
thanks. A couple online questions.
Oh, cool.
Yeah, one's from Stephen Mayer, who asks, what do you use to monitor your own apartment?
My house?
Yeah.
I do the same system. I have, so when we first started looking at or started thinking about monitoring the actual energy use of our projects, my house was the first one to be set up with the system. And my 2 years is almost up, so mine's going to get uninstalled and go on to another project soon. The difference in my house is I only have 14 circuits, and some of these projects are like nearing 100 circuits. So it's a slight scale difference. But even as somebody who thinks about energy all the time, I learned so much from monitoring my own house, both about my systems and my habits. And probably the most interesting thing is that when I'm not home, my whole house runs at 63 watts. And 63 watts is my thermostat, my wireless internet, and my e-monitor, which uses like 12 watts. Which is exciting because then when we have residential clients, when they're not home and their house is burning 1,000 watts, we can show them that it's possible to run at kind of something very, very, very low, much lower than that.
And, one more question from online. Is there a specific reason for using Severa or simulation versus simulation like Green Building Studio or Energy Plus?
So the more complicated programs like Energy Plus, I'll use those for our residential and commercial projects. There's only a few people in the office who know how to use these tools. Sapphira, which is, again, not the best energy modeling tool in the world, but has a very, very simple user interface, and you can answer some very, very basic questions with it. And what I found is that the level of energy modeling knowledge among typical architects, even architects who were just out of school, who presumably had some sort of environmental class, was not really very high, and that many architects and many very, very talented architects who went to really good schools don't really know what about the building impacts the energy use. Basically all the inputs that you would have in energy modeling piece of software. So one thing that I wanted to do was kind of open up, kind of take energy modeling instead of this little kind of closed off thing that I do at my desk and then I go back to you and tell you about the results that I came up with, kind of allowing project teams to experiment with some of these variables, right? If I rotate the building, what does that do? If I increase the insulation value, what does that do? If I have a building that's kind of long and skinny as opposed to small and compact, and it's in this particular climate, what is that? So Sapphira has been incredibly useful for bringing a typical architect who doesn't maybe have a lot of specific interest or knowledge in modeling, kind of to understand the basic inputs and allow them to make more informed decisions, but also their intuition becomes better. But it's not a tool that I would recommend using for digging in and getting some really sophisticated problems. I mean, you would never, and there's no even like inputs for mechanical systems. So it's really an envelope modeling tool.
One more burning question. Oh, there's one. Do you read BSUG?
I just started experimenting with BSUG recently, and I'm really, really excited about BSUG. So I don't have the proficiency. I haven't used it on a project yet, and I've been playing with it on little sample projects that I've been building. And what's so exciting about BSUG is that it includes cost into the equation. And are people familiar with BSUG? Somewhat. So what's cool about BSUG is basically it has this basic assumption where you have a typical building, and if you imagine a curve, I'll try to draw a graph in the air. You have cost against energy use, and a typical building might start here. And initially, cost decreases. Sorry, this is energy efficiency. Cost decreases and energy efficiency increases at the same time. So by making a few kind of simple adjustments, not only does the project get cheaper, but it gets more energy efficient. And then, as you get more and more efficient, you start to curve upwards, and that's when you have more expensive technologies where it takes more money to get increased energy uses. But by the time you're back to where you started in terms of the cost curve, your energy efficiency is really, really significant. And you can even go a little bit further because people expect to pay more for an efficient house. So what BSUG, hopefully, in theory, what it allows you to do is optimize the cost and the energy both together. So the initial energy use reductions are all the cheapest, and then you can kind of really, really specifically focus on some of the more expensive ones on the set. So I think I'm really excited about this tool, and hopefully we're going to be able to start using it pretty soon. So, have you used it?
Yes.
Yeah.
I haven't done a lot of the talk, but
What are your thoughts?
I like it. We actually we're using it to develop power tools, but it's on the residential side, so we haven't done a lot of it, but been using it on some Idaho Power, basically internal tools. But it seems powerful. It's great that it's front end to Energy Plus, which we trust.
and then has a lot more capability, I guess, with an easy interface. Yeah, we like it.
Cool. All right.
Thank you. Maybe a good one. And again, don't forget our good friend Jake's back next month to impress us all with his work at EDR. Apparently EDR is producing great minds. Well, IDL and EDR are producing great minds. So we look forward to seeing you guys here for that. Grab some chips on the way out. There's always extra. Please fill out the evaluation forms if you have a moment. Helps us. And feel free to send any feedback you have about this or other things we should be doing or are doing right. Send those comments our way. We'd like to hear them.